I'd like to work example 9.11 out of section 3 of chapter 9 for you to get us a little bit of introduction in what it is that we're doing here. You may recall back in chapter 2, we said that the heights of young women was normally distributed with mean 64.5 inches, standard deviation 2.5 inches. So I want to know, if I select one woman at random, what's the probability that this woman has a height greater than 66.5 inches? Or, in other words, in graph form, if the mean is 64.5, standard deviation is 2.5, what's the probability a randomly selected woman would fall in that range? The next thing I'm going to do is standardize it. So that's the probability Z is greater than 66.5 minus the mean over the standard deviation. That's, you can work it out on your calculator, or trust me, the answer there is 0.8. And if I use the pink chart or my normal CDF, I find that to be the shaded probability. If you got 0.7881, remember that's the area to the left. We want the area to the right. So there's about a 21% chance that if I select a woman at random, she'll be taller than 66.5 inches. Now what if instead I choose 10 women? What's the probability that their average height will be greater than 66.5 inches? Well, we know this should be different than the problem we just worked. Getting one woman taller than average, 2 inches taller than average, is not particularly strange. But now getting an average of 10 women that ends up 2 inches above average would be a little more unusual. Let's work this problem. As it turns out, this new distribution, this sampling distribution, if you will, has the same mean as before. We started out in the previous problem with a normal distribution spread 2.5 inches, or standard deviation 2.5 inches. This next problem will remain normal, but have a smaller standard deviation. Now in the first section, we said the standard deviation of p hats was the square root of p times 1 minus p over n. This problem, on the other hand, is not a p hat, but rather an x bar. Standard deviation of the x bar is sigma, the original standard deviation, over the square root of 10. So in this case, the mean of our new sampling distribution, the one where I'm not looking at one woman, but rather I'm looking at 10 women, has a normal distribution with the same mean as before, and a standard deviation that's now not 2.5, but rather 2.5 over the square root of 10, which in this case means normal with mean 64.5 inches, standard deviation of about 0.79 if you work that out. So now the probability that I get an x bar bigger than 66.5 is still standardized, but now the standard deviation is not 2.5, but rather it's 2.5 over the square root of 10, which we just said was 0.79. I know I'm going fast. Purpose is for you to get an idea of what's going on. This is also example, as I said, 9.11 out of your text. It's on page 517 and 518. When I standardize that, I get 2.53. Notice that z-score is much bigger than the z-score we had here, 0.80. Which means this is more standard deviations from the mean, which means this is more unusual. In fact, this probability is less than 1%, 0.0057.